Okay, time for you guys to work through one on your own. So here's what that problem is. So here's the balance, or the skeleton. I shouldn't say it's not balance. Here's our skeleton reaction here for permanganate anion reacting with oxalate anion to generate manganese dioxide and carbonate anion. So one of the things I want to make sure to highlight for you guys is, because we're bringing back a lot of polyatomic ions, make sure you're doing your work not only to practice for the final exam, but it's important for this chapter of making sure that you're good with naming species, because you are going to see problems that have you have to think about just chemical names rather than looking at a chemical formula. Notice that this one does ask us to balance in basic solution. All right, so what I'm going to do, and again, I'm sure you could have this sheets in front of you to walk through the different steps. I'm going to tell you what the step is, and then I'm going to ask you to pause the video and try to work through it on your own. Okay, step one is to take our skeleton reaction and divide it into two half reactions. Again, looking for things that are related by non-oxygen or hydrogen atoms to find these redox pairs that will create an oxidation and a reduction half reaction. So go ahead and pause and try to figure that out for this problem. All right, hopefully we see that the manganese should go together. So our permanganate anion, and then our manganese dioxide, and then our carbon and oxygen here, specifically our carbon here. So we've got carbon with oxalate and then carbon with carbonate. So first step is pretty simple, just taking and dividing out, and again, we don't need to think about phases or anything at this point, but separating our skeleton equation into a reduction and an oxidation half reaction. And at this point, we don't necessarily know which is which. All right, moving on for the next step. This is going to be the most involved because it has to do with balancing atoms and charges. So remember, first go through and balance atoms other than oxygen and hydrogen, then balance oxygen by adding water, balance hydrogen by adding H+, and then balance charge by adding electrons. So go ahead and pause the video and see if you can figure that out for both of these half reactions. All right, so what I've got shown here in red is what we'd use to balance the oxygen and hydrogen atoms. Okay, for this guy, I had already written it right here. There was a 2 that was there that actually shouldn't have been there because it wasn't part of what we had here. But we're going to have a 2 that gets added here to balance our carbon atoms. And then we didn't have to do anything to balance the manganese here. But when we think about balancing the oxygens, we need to add 2 waters to account for the 2 oxygens that are over here. And then again, we've got 4 oxygens that are over there. I should have said we've got 4 oxygens over here, 2 that are here. So we need to add 2 waters to finish balancing those oxygens. And because we added 4 H pluses that we have over here, now we're going to add 4 to our left side here. Coming over with our oxalate and our carbonate here, we could look and see that we've +got 6 oxygens that we have here, 4 already on this side, so we're going to need to add 2 waters. Adding 2 waters means adding 4 H+. Go through now and balance our charges. Again, nothing is charged over on our product side here, so the net of everything over there is 0. We've got 4 +1 things and 1 -1 thing, so that ends up being a net of -3. To have it equal a net charge of 0, we're going to have 3 electrons on our left, so this guy is our reduction half reaction. Looking over here on the right, we're going to have, again, no charge contribution from water. 1 oxalate anion contributes a -2 charge. And even though we've got 2 carbonates at -2, we've got 4 H pluses at +1. So the net of everything on this side is 0 as well. Note over here it was 0 because everything was neutral. Over here it just happens that they cancel out. So to have -2 equals 0, that means we need to have 2 electrons on the right side. All right, remember step 3 is going to be looking at these half reactions. So again, 4H plus MnO4 minus plus 3 electrons. This reduction half reaction has 3 electrons. This oxidation half reaction only gives up 2. So we're going to need to do some scaling here so that what's given up in our oxidation reaction is equal to what's taken on in our reduction half reaction. So go ahead and pause the video and see if you can figure out how to scale these reactions up. All right, hopefully you see here that this is one where we actually have to scale both of them because the common factor is going to be 6 electrons. So we're going to multiply each of these by a factor that allows us to get to 6 electrons. So again, our reduction half reaction, which we have shown right here, okay, when we took and we summed up all of this, we need to scale this up by 2. We need to take this guy, which was our oxidation half reaction, and we need to scale that up by 3. I'm going to have that on the next slide. And remember, the next slide, our last step in balancing an acidic solution is just basically to add together our balanced half reactions and include states of matter. So one of the things to take note and to think about here is in this particular example, we have one half reaction that has water as a product and another half reaction that has water as a reactant. Same thing with H pluses appearing on both sides. So remember, we want to have the net of water and H pluses. So think about what those nets might be. See if you can figure out what the overall summed and now balanced redox equation is here. All right, so again, a lot that we have here. If we're looking at 8 H pluses, and again, we're kind of scaling up this guy where I'm doing summing and kind of scaling at the same time. So 8 H pluses, 2 MnO4s, and again, we've got then 6 waters and then 3 oxalates. That's how we get all of our reactants here. All of our products are going to be 2 MnO2s, 4 waters, 6 carbonates, and then 12 H pluses. But remember, we already noticed that there's going to be water on both sides and H plus on both sides. So what I've done now is said, you know what, if I had 6 on the left and 4 on the right, the net is going to be only 2 on the left. Same thing with H pluses, 8 on the left, 12 on the right means there's a net of 4 on the right. So summing and putting all of that together here is our balanced redox reaction in acidic solution. Just as a good sort of practice, one of the things that you can make sure to do is go back through, count all of your atoms. Everything should balance in that regard. All right, the last piece is to say, oh, this asked us to do it in basic solution. Remember the steps and the directions for balancing in basic solution are we have to find out where the H pluses are, and we're going to add the same number of OH minus ions to both sides of our half reaction. That, again, allows us to make sure that it stays balanced. When we add H plus and OH minus, that's going to generate water. And then again, we'll have to reconcile where we have a net accumulation of water. So go ahead and pause the video and try to finish out this problem in basic solution. All right, we had H pluses that were on the right side of our equation here when we were in acidic solution. So we had 4 OHs that we needed to add in order to neutralize that. We have to make sure to add 4 OH minuses to the left as well. When we add 4 OH minuses to the side that has 4 H pluses, that generates 4 waters. Remember, we had 2 that were on the left. So 2 on the left, 4 on the right is going to net us 2 on the right. So now rewriting everything, accounting for the fact that we've added 4 OH minuses to the left, and we have net now of 2 waters on the right, we get this final balanced chemical equation, balanced now in basic solution. So conceptually, not really super difficult here, but it's just one of those things that we just got to make sure we keep track of all of our steps and all of our species along the way so we get to the final correct balanced chemical equation.